Welcome back. Today's topic is application of Ampere's law for determining magnetic fields. In the last video, we have seen the statement of Ampere's law, and before that, we have seen magnetic forces on current elements. And in this video lecture, we will see how to apply Ampere's law to compute magnetic field intensity and also flux density for different current configurations. Okay. Let's start with the basic statement of Ampere's law. It states that line integral of tangential component of field intensity around a closed path is same as the net current enclosed around the path. And we do have a differential format also of Ampere's law, which is the Maxwell's third equation, del cos H is equal to J. Now, applying this one for determining the magnetic field intensity vectors. The very first equation, determine the magnetic field intensity due to an infinitely long conductor carrying a current I at a distance of h using Ampere's law. We have done this problem in other ways and we have determined that h is equal to I by 2 by h or 2 by a. Right, now we will try to develop this equation using Ampere's law. Now see here, now consider this is a 3-axis phenomenon. This is z, this is x, and this is y. Now consider an infinitely long conductor which is carrying a current in this fashion in z-axis. Okay, and let P be the point here at which the field is to be computed. Here I need to determine the field. It is at a distance of h from the current element. This is the current element. H is the shortest distance from this current element. And now I am drawing a closed path P around the conductor, which I call it as an Ampere path. Okay. This is a closed path around P. Normally what I do is nothing but I will do concentric circles around with this line conductor as a center. I'll draw a concentric circle, and this is called as an Amperean path. So it is just like this is my conductor and I have drawn a path like this, and it is carrying I, and this is my point P, which is at a distance of h. Now we know that by Ampere's law I is equal to line integral of h dot dl, right? In the above axis, if you carefully see, right, this is h, right? This is I, and the axes are like this. This is z, this is x, this is y. I is along the direction. Now, if you carefully see h will be in this direction, right? Now, if I take it as a conductor, now if this is my field, if it is moving in this fashion, then what I should do, I should consider my field. It is moving, right? So I'll take it as h is having phi components, because see what it is varying, distance is common, what it is varying, angle is varying. So I'll take it as h is having h phi component and it along phi axis. I'll take it in cylindrical coordinates. Okay, h is equal to h phi u phi. And differential length. Now if I consider a small differential length here, I'll write it again. Right, if I consider this small differential length, you know that this is h, right, the shortest distance, what we call it as the radius in this case, and let us suppose this is the angle theta. You know that L is equal to r theta. I think you remember this famous formula from your geometry or in a circle. So here in this case my L is nothing but dl, my radius is nothing but h, and this is my d theta. So if I write it as a vector now, dl is also h, here it is phi into u phi. Now this is my magnetic field and this is my dl vector, differential length vector. Now I'll substitute these two things here. So what I'll be getting? Yeah, this is my h, this is my dl. See u phi dot product, it gives 1. So what I'll be getting? I'll be getting h phi, h d phi. This is the field component in phi direction, and this is the differential length. Now, if you see, these two are basically which are independent of phi. So I'll write it as h is equal to h phi h integral of d phi over phi. So what is this? If I consider this as phi, what is this value of entire differential integral of entire phi? This will be 2 pi, right? So if I substitute it here, what I'll get, h is equal to I is equal to h phi into h into 2 pi, isn't it? So this is what I have written here. I is equal to h phi h into 2 pi. So if I want h phi as a subject, what I'll do, I'll convert these things. I'll send these things to here. Right. If I write it as a vector, it is having only component along this phi direction, so I'll write it as this one. So this is what we have obtained in other ways also. This is the way how we apply Ampere's law to determine the magnetic field intensities. Now if I want B, right, this is also just like in this fashion. Right. Now let's try for one more. Develop an expression for magnetic fields intensity both inside and outside a solid cylindrical conductor of radius A carrying a current I with uniform density, and sketch the variation of field intensity as a function of distance from the conductor axis. Which means that he wants to determine expression for magnetic field intensity both inside and outside a solid cylindrical conductor, which means that there is a solid cylindrical conductor. This is a conductor. And he wants to determine from the center up to the surface and up to outside the value also. So I'll take it as better, I'll take it like this, cross-sectional area, right? This is my entire conductor, cross-section. So he wanted at the center and up to here and also up to here also. So I will divide it. We have done it in electrostatic fields also. I'll divide it. This is inside the conductor. This is case B. This is on the conductor, and this is outside the conductor. This is case 1, case 2, and case 3. We'll divide it. And this is solid conductor, right? Solid conductor means current will be flowing inside also. If it is a hollow conductor, then it will be flowing on the surface. But since it is a solid conductor, we need to calculate the current every time inside also. So for this one, what I'll do is, let J be the uniform current density, which means that if this is the conductor, right, this entire current which is flowing is I, right? So if I want only up to this area, what I should do? So for this entire area I, it is right. So what is the current density? I'll take this J is equal to I by, what is the surface area of this one? Pi A square. Assume A is the radius of the conductor, okay? Into, if I want only up to R, what I should do? I dash is equal to J into pi R square. What is J already? It is I by pi A square. So I dash is equal to I R square by A square. Right? On the surface, automatically what will get? R is equal to A. So I'll get again I. If R is equal to A, then I dash is equal to I into A square by A square. It is I itself. So this is the format which will be employed. Okay. So for case 1, for R is less than A, what you will get? For R is less than A, the current for radius R with current density, this is the formula which we have already done. Right. So magnetic field intensity we have already obtained earlier, right? This is the expression. H is equal to, now what is the current? I dash is the current for anywhere R. This is actually A. For anywhere R is less than A, this is the expression, right? So considering, if I consider only the magnitude, I'll remove this component. I'll write it as only H is equal to I dash 2 pi R. You know I dash already, right? What is I dash? I into R square by A square, right? So if I 1 R I'll go, what I'll get? I by 2 pi A square R. This is field component, field magnitude inside the conductor. If you see, this is constant, this is constant. What is varying? R is varying, which means that if this is the conductor, this is A, for up to here, the field will be slowly increasing up to the surface because H is proportional to R. So directly proportional to R. Now case 2, what I will be getting here? If R is equal to A, my current I do have I, right? So I will take it as I by 2 pi A. So on the surface, this is my field. See, it is independent of R. It is dependent only on A, right? In case 3, for value R is greater than A. So this is my conductor. During this region, it was region 1, it is region 2, and here it is region 3, right? Here it was proportional to R, here it is independent of R, and here again the formula will be H is equal to I by 2 pi R, because the current was only I itself, that is, even at this point if I consider. What is the current enclosed? Only I is the current enclosed, right? I by 2 pi R. So what is increasing? R is increasing. Now H is proportional to 1 by R. So if I sketch these things, see, this is my surface. Up to here it is surface. This is region 1, this is region 2, and this is region 3, outside my conductor. So here it was linearly increasing, it reached its maximum value, and again it is inversely proportional. This is H is proportional to R. Here it is H is independent of R, and here it is H is inversely proportional to R. Directly proportional to R, independent of R, and inversely proportional to R. This is my field distribution. Okay. Now, moving on to the next one now. We will do one more problem today. Now, a single phase circuit comprises two parallel conductors A and B, 1 centimeter diameter and spaced 1 meter apart. Which means that there are two conductors. Each is having 1 centimeter diameter, which means 0.5 centimeter is the radius. And the conductors carry 100 amperes and minus 100 amperes. Determine the field intensity at the surface of each conductor. So here he wants H, here or here. They are spaced at 1 meter apart. This is a separation between them. Determine the field intensity at the surface of each conductor and also in the space exactly midway. Here also he wants the fields. Okay. So now we do have two conductors, right? At any point, this will be having field and this will be having, this is HA, this is HB. HA and HB. At any point, the resultant field is a vector sum of these two. Right? And if you carefully see, HA is nothing but 1 I by 2 pi R1, it is I by 2 pi R2, and both will be having vectors. Right? If you carefully see, the field produced by each conductor is directed downwards at any point. See, this also will be in this fashion and this also will be in this fashion because both the currents are 100 and minus 100. So anyways, both they will be acting in the same direction. So what I will do between these two, it will be directed downwards, it will be directed downwards. So I will directly add these two terms. So this is why I have taken it as common, I by 2 pi, 1 by R1 plus 1 by R2. Okay. So at any of the conductor surface, if you carefully see, this is 100 by 2 pi. Now at this point, if you carefully see, what is the at this point from this, what is the distance? It is 0.5 centimeters, right? So which means that R1 is equal to 0.5 centimeters, which is nothing but if I convert it into meters, This is R1. I is nothing but 100, and R2 is nothing but 1, right? Because at this point it is 1 meter nearly, right? So I'll take as approximately as 1 meter. So 1 by. So if I substitute, I'll get this value. Now let us suppose if I take it is in the middle of this line. So what I'll get from here, it is 0.5 meters. Here from here it is 0.5 meters. So R1 and R2 both will be 0.5, 0.5. So this is the answer, right? So this is the field distribution. If you see at surface, it is 3120. At the middle, it has reduced to very low value. And now again, if I go to here, again I make it 3120. So how the field distribution will be? The field distribution will be like this. On the surfaces, it will be maximum. If I go into the middle, value will be decreasing. Okay, and again it will be increasing. So this is the way how we solve the problem. Okay, so that's it for today. We will discuss again more problems in the next class. Thank you. I hope now you are able to compute magnetic field intensity and flux density for different current configurations. And this is a practice problem. Try to solve this problem at home. We'll discuss more problems in the next class. Okay, thank you.